Hello everyone, how are you all doing? Hi there, my name's Robert Palgrave, as you can see by my name tag below my face. And welcome to this first ever stream, this first proper stream of the Journal Club Twitch channel. So I'll spend maybe a minute or two just describing what this channel is about, because nobody's ever seen it before, and maybe this kind of channel doesn't really exist. I don't really know. I haven't been able to find anything exactly like this on Twitch. So let me tell you a bit about the channel, and before we kind of get into the stream and try it out. So the idea behind this channel is that it is an online or a Twitch journal club. So a journal club is somewhere where people get together and they discuss academic journals. So they discuss articles that have been published recently in academic journals, and they read some of the articles and then they discuss some of the ideas contained in those articles. So that is the idea of this Twitch stream. It's to really replicate what goes on in many universities, in many research institutes, in many scientific societies, in many clubs throughout the whole world, but on Twitch. So hopefully, as the channel develops, there'll be people watching, and there'll be people joining in, and people contributing to the discussion about different papers. So I'll tell you a bit about myself. My name is Robert Palgrave. I'm a professor at University College London, UCL, which is a big university in the middle of London, in England, in the UK. And my speciality, really, my expertise is in chemistry, and specifically inorganic chemistry, materials chemistry. So really, those are the kinds of papers that I'm going to be talking about. Those are the kind of journal articles that I'm going to be discussing. But who knows, as the channel evolves, if the channel does evolve, we may be able to have other presenters and branch out maybe onto other topics as well, apart from just materials chemistry. But you know what? I think materials chemistry is a pretty exciting topic. I think there's a lot of really interesting things going on there. There's more than enough to be keeping us occupied, even if we never change to a different topic at any stage in the channel. So, in a nutshell, that is it. We're going to be chatting about some papers. I'm going to be giving you my views, and if anyone logs on and wants to give their own view, that would be fantastic. Just contribute via the chat, and we can get a bit of discussion going at some point maybe. But this is the first stream. It's highly unlikely anyone's going to be watching. So for now, you're just going to have to put up with me talking about different papers. So I should say we've got probably a couple of papers we'll try and go through today. I'll try and go through them in a little bit of detail, and maybe kind of expand around some of the ideas there. If you do want to find out more about me, I'm highly Googleable. I am search engine optimized. You can Google my name, and most of the results will be about me. So you'll be able to find out more about my background if you want to find out anything about that. You might even want to read some of my papers, but you know, let's not go too far. I won't be reviewing any of my own papers. I don't know, maybe one day I should review my own papers. That'll be interesting. But for today, we're going to be looking at papers from other research groups, which are far more interesting. So that's probably all I have to say right now as a introduction. Maybe the best way to understand a channel is to do the channel. So maybe we should do the channel. All right. So I have a paper lined up for you guys, and the first paper that I have lined up for you guys is this paper here. So it's called Towards Exotic Layered Materials 2D Cuprous Iodide. And this is a paper published, although you can't see it because my face is in the way. Do I have something without my face? Let's see. I don't think I do. Maybe I need to make a new screen without my face at all, so you guys can see it a little bit more easily. But anyway, this paper is published. I'll scroll down a bit so you can see. This paper is published in a journal called Advanced Materials, which is one of the leading journals in materials chemistry, materials science. It's published quite recently. It's actually, I think, in the latest edition or a very recent edition of Advanced Materials, and it is an open access paper. This paper is free for anyone in the world to read. Maybe one day we'll have a stream about journal publishing. What's the right word? Journal publishing landscape is kind of landscape is a neutral word, isn't it? The journal publishing landscape, and we can discuss, how journal articles get published in science, who pays for them, who can read them, things like that. It gets a little bit political, but we're not going to do that today. We're going to just talk about the science. So this is an open access article. Anyone in the world, if you have an internet connection, and if you're watching me, you probably do, can Google this title, and you'll be able to find it, and you'll be able to read this article, and absorb the information it contains. So this article, the lead authors here are from the University of Vienna in Austria, and there's also other contributions from research in Germany, in Belgium, and in Slovakia, and in France. So there's quite a wide collaboration on this paper. So let's have a little look at the abstract. So the abstract is just a summary of the main findings of the article. It's kind of like the article in ultra condensed form. So let's have a little read through this. Heterostructures composed of 2D materials are already opening many new possibilities in such fields of technology as electronics and magnonics, but far more could be achieved if the number and diversity of 2D materials were increased. So far, only a few dozen 2D crystals have been extracted from materials that exhibit a layered phase in ambient conditions, omitting entirely the large number of layered materials that may exist at other temperatures and pressures. This work demonstrates how such structures can be stabilized in 2D van der Waals stacks under room temperature via growing them directly in graphene encapsulation using graphene oxide as a template material. Specifically, an ambient, stable 2D structure of copper and iodine, a material that normally only occurs in layered form at elevated temperatures between 645 and 675 Kelvin, is produced. The results establish a simple route to production of more exotic phases of materials that would otherwise be difficult or impossible to stabilize for experiments in ambient. Okay, so as we hear there, the paper is about stabilizing 2D materials. So 2D materials have become pretty famous. One of the, if you probably ask someone to say name any hot topic in material science, materials chemistry, condensed matter physics, a lot of the answers you're going to get back, even to this day, are going to be about graphene. So graphene is kind of shot to global fame with the awards of the Nobel Prizes in the early 2000s for the discovery of this material. So graphene, of course, is just a single layer of graphite, and graphite is one of the important polymorphs of carbon. The main other polymorph of carbon, of course, being diamond. So graphene is just a single atom thick layer of carbon, and in many ways it's kind of one of the prototypical 2D materials. So it consists of a single layer of atoms. You can't really get more two-dimensional than that, so you reduce one of the dimensions really if this material as small as it possibly can be. You can't really go below one atom. People do argue about this. I have seen some, maybe we'll have a look at that later on today if I remember. People have argued that the name 2D is not really appropriate for these materials because even an atom has an amount of thickness. An atom is a 3D material, so how can you make a 2D material out of a 3D material? But I'm prepared to accept that and I don't think you can avoid it now. The name is in the literature. It can't be, the genie can't be put back in the bottle. These are known as 2D materials, even though they're made of three-dimensional atoms. So graphene is the kind of prototypical 2D material. But there's lots of other materials like graphene as well. So there's things called transition metal dichalcogenides. So for example, molybdenum disulfide. This is a material which exists in its normal form. If you make molybdenum disulfide and you just have it as a powder or as a crystal, it's a layered crystal. So similar to the way that graphite is a layered crystal. It consists of layers of these carbon atoms, and to form graphene you can just take a single one of these layers off. Similar idea for transition metal dichalcogenides. They exist as layered structures, and you can just separate, you can exfoliate or separate somehow one of those layers, and it becomes then a 2D material. So the point they're making here is that most of the 2D materials we know about, so graphene, transition metal dicalcogenide, even things like phosphorine, are based on separating already existing layered structures. So there's a layered structure that's already stable, and you just separate one layer from that. What they're saying here is that there's actually other ways to get 2D materials. So what they've managed to achieve here is they've got a, as we'll see as we explore the paper, they have a 2D, they have a single layer of a layered material. So this copper iodide or cuprous iodide does form a layered structure, but the difference is it only normally forms that layered structure at high temperature. So the normal room temperature structure for cuprous iodide is a three-dimensional structure. It's based on zinc blend, so it's a cubic structure, which can't be separated into layers. But what they've done in this paper, they've stabilized single layers of the high temperature polymorph of cuprous iodide, and the way they've done that, they've sandwiched it between layers of that material we talked about earlier, graphene. So they've used graphene as kind of like the bread, and their cuprous iodide is the sandwich filling, whichever sandwich filling you prefer. Could be cheese, could be meat. The cuprous iodide is that part, and that's how they've managed to stabilize this layered form of cuprous iodide by encapsulating it between sheets of graphene. Okay, let's have a little look in the introduction, and they kind of say similar things to what I said there. So current 2D materials largely derive from van der Waals layered bulk structures. That in kind of one sentence is what I've just spent about 5 minutes trying to say. Van der Waals bulk structures, they mean structures where you have layers, where you have strong bonding within the layer. Could be covalent bonding, could be ionic bonding, but between the layers you have much weaker bonding. You have these van der Waals forces, van der Waals bonding, which is much weaker form of bonding. So that means the layers are kind of easily separated. Okay, such structures exist under, I'll read the bit behind my face. Such structures exist under ambient conditions, and in total, however, only a limited number, there you go, that makes sense. Only a limited number of such structures exist under ambient conditions, and in total only a few dozen 2D crystals have been successfully synthesized or exfoliated. So exfoliated, just separating the individual layers from the bulk structure. While the unusual properties of graphene make it an interesting object of investigation itself, yeah, you can say that again, there's probably 10, 50, maybe 100,000 papers on graphene. It can also serve as a substrate, to stabilize other less obvious 2D materials. These include materials that do not by themselves form 2D phases, such as covalent silicon dioxide, SiO2. Okay, that's kind of interesting because I haven't seen that, so maybe I'm going to follow up that paper. Pseudo-ionic PbI2. So PbI2 is kind of a layered structure anyway. But yeah, okay, that's interesting. And metallic copper gold alloy. Okay, so maybe references 2 and 4 here. They might be worth kind of following up for me at least. Maybe I'll do it on stream, maybe I'll do it afterwards. Making single layers of SiO2 sounds pretty interesting. The alloy, I don't know. I mean, if you take gold, you can literally beat it into a single layer with a hammer if you have the patience. So still, want to use graphene instead of a big hammer? That's great. SiO2, I'm pretty sure you can't beat SiO2 into a single layer with a hammer. You know, get a bit of glass, hit it with a hammer. It's not going to work out well. In the same spirit, layers of graphene have also been used to encapsulate materials. Okay, great. Oh, was this not talking about graphene up here? Okay, well I thought it was talking about graphene. It seemed to suggest this tendency was changing topic, but anyway. Layers of graphene have also been used to encapsulate materials. Metal atoms, in some cases forming nitrides, have been intercalated between monocrystalline SiC, a silicon carbide surface, and graphene to produce 2D metamaterials. Okay, interesting. In other studies, the encapsulation strategies have been applied. In situ transmission electron microscopy TM, observations of dynamics in liquids. Okay, sure. So you can flow liquids through between very, very thin layers. you know, a very narrow channel formed by 2D materials. Could be silicon carbide. I think it normally is silicon carbide. So you can flow liquids between those, and you can do transmission electron microscopy. You can do TEM kind of perpendicular to that. So it's this so-called liquid TEM. In fact, we have a liquid TEM at UCL chemistry department, which I've never used, but as far as I understand, that's what it does. So you can do transmission electron microscopy of a liquid, which is pretty unusual because TEM is a high vacuum technique. Most liquids are not stable in a high vacuum, so you can't really do TEM of them. But using this kind of encapsulation method, this silicon carbide method, apparently you can. But that's a different topic. Maybe we'll look at some papers on that in the future. In addition, the inert and impermeable graphene envelope can also stabilize 2D layers of weakly bound molecules and atoms and islands of C60 fullerenes and noble gases have been observed in graphene encapsulation. So yeah, there was actually some work from my colleague Christoph Salzmann at UCL chemistry using carbon nanotubes. So a similar idea, except, you know, even less dimensionality, going from 2D down to 1D material. So carbon nanotubes are long tubes of carbon, and inside those you can put things. So here's work on Professor Christoph Salzmann, Professor Andreas Seller. There were probably some other people involved as well. Maybe I'll look up their paper in a minute. I've got given myself lots of things to do later in the stream. Who knows what I'll remember. They put in phosphorus, so they put phosphorus atoms into a carbon nanotube, and they managed to stabilize a different polymorph, a different structure of phosphorus, which hadn't been seen before. I think they called it pink phosphorus. So I'll definitely try and maybe I'll do it now. Who knows? Let's have a go. Let's pink phosphorus. Let's have a look. Yeah, this could be it. Pink phosphorus. Let's go. Salzmann, UCL. Yeah, probably. Let's click on the right thing. Maybe try this link here. I have no idea where this link's going to take me, so this is exciting. First studying pink phosphorus in caged carbon nanotubes. Yeah, a new form. This is back in 2017. It's a long time ago now, isn't it? 5 years ago. A new form of phosphorus made up of a chain of highly reactive white phosphorus molecules isolated inside single-wall carbon nanotubes have been discovered by UK scientists. Let's see, do they have the picture? They don't have a picture. Okay, well, that's kind of that's not so good, is it? Or do they have the hang on, encapsulation, polymerization? This is probably. Do they have the picture here? This is a single-wall carbon nanotubes have been used to encapsulate many types of materials, but now other nanostructured phosphorus allotropes are attracting considerable attention. It'd be good if they just had. Oh, there we go. Full article in Angevante. Let's see if we can log on to this. We might need to. Yeah, here we go. Okay. Putting P's into a pod. So tetrahedral P4 molecules can be assembled inside single-wall carbon nanotubes. So there we are. Here's an artist's impression of a carbon nanotube with P4 molecules or P4 units, because I think they're all joined together. So it's kind of a polymer really. P4 units encapsulated within it. Okay, and I think the match is to kind of tell us that they are phosphorus is using matches. Okay, let's see if Wiley will allow me to log on. Yes, let's do it. Log on. I need to update my password on Edge. Let's see if this works. No, you're fine. Let's see if we can get there. We have the famous. Oh, you can't. It's not on your screen. We have the famous coffee cup filling up. There we go. Encapsulation, polymerization of white phosphorus inside single-wall carbon nanotubes. So yeah, Christoph Salzmann, Milo Schaefer, Andreas Seller, Angelos Michaelides, lots of other people involved here. So yeah, this is the main image, I guess. So we have a That's a beautiful TEM image, isn't it? So we have the carbon nanotube, and inside you've got these little peas in a pod, and there's the kind of artist's impression of what it really is. It's the P4 units, 4 phosphorus atoms joined together and stringing along inside this carbon nanotube. Very nice, and they do a lot of characterization. So there's some XPS. We might be talking quite a bit about XPS in this stream. It's one of the things that we like to do in our group. More images of this. Okay, so this is kind of another a similar kind of idea to the paper we're talking about. So the paper we're talking about, remember, is about 2D materials sandwiching graphene. This paper here is about 1D materials inside a carbon nanotube. So it's kind of a similar idea. It's really using carbon to encapsulate and to change the structure of already existing materials, to force them to adopt a different polymorph. So in this case, we're not talking about phosphorus in the paper. We're talking about, let's just go back to the title so you guys can see it. We're talking about cuprous iodide. Okay, so they've kind of told us that there's other ways to encapsulate stuff. We had a little diversion and talked about the phosphorus encapsulation inside a one-dimensional chain. So yeah, the concept of encapsulation is not limited to mere van der Waals forces. Indeed, it entails a much greater variety of similarly constrained 2D structures in a bulk form exhibit a van der Waals layered phase only at either elevated temperatures or pressures. One such material among countless that have been predicted is the beta phase of cuprous iodide that is only stable at a narrow temperature range, very narrow temperature range, 645 to 675 Kelvin. And therefore exfoliation and monolace in such crystals would be rather complicated. Well, I guess so. I mean, you'd have to get this phase stabilizer between these two temperatures, and then try to exfoliate it at that temperature. Probably a pretty difficult experiment, maybe not impossible, but I would say probably pretty challenging. The 3D gamma phase of cuprous iodide, in contrast, is stable at ambient conditions, has been known for its high Seebeck coefficient, useful for thermoelectric materials, and appreciable optoelectronic properties. Appreciable, this is a good phrase, appreciable optoelectronic properties. Basically, it can do anything as long as it kind of absorbs light and does something, maybe conducts and charge. It's got appreciable optoelectronic properties. It covers a lot of bases with that phrase. Extremely thin layers of this non-layered cubic gamma phase of cuprous iodide have been successfully prepared and combined with 2D tungsten sulfide, disulfide. So this is one of these transition metal dichalcogenides, and tungsten selenide, another one of transition metal dichalcogenides. Nevertheless, the truly 2D phase of cuprous iodide, to our knowledge, has not been prepared, and its properties remain unexplored. In fact, 2 distinct configurations of the 2D cuprous iodide structure were recently predicted by these guys. I'm guessing in a theory paper. I haven't read that paper. Both unstable at ambient conditions, and our primary motivation in this work therefore was to find out whether and which of the predicted structures could be synthesized. Okay, so cuprous iodide actually, as I was doing a little bit of reading through this paper, it's got a very complicated set of structures. There's a lot of different structures for cuprous iodide. One of them is this layered form. The stable one at room temperature, however, is a cubic form. So it's actually similar to the structure of diamond. We'll maybe have a look at the structures in a minute. But the layered form, in theory, could be exfoliated and made into a 2-dimensional material the same way as graphene, the same way as transition metal dichalcogenides that they mention here. And the challenge, though, is that it's only stable at high temperature, so 645 Kelvin, pretty high temperature to be doing these experiments. Could be some practical difficulties in doing that. Probably not impossible, but there's practical difficulties. So they're looking for a different way to stabilize this material at room temperature. Okay, and they do this basically by sandwiching the high temperature. They call it a van der Waals layered. I don't actually, maybe we'll come on to that in a minute. I don't know whether beta cuprous iodide is really a van der Waals layered compound in the same way that transition metal dichalcogenides are, or even graphene is, or graphite is. But anyway, maybe I'll expand on that maybe in a minute. But anyway, whether it's van der Waals layered or not doesn't really matter. they want to stabilize a single layer of cuprous iodide at ambient conditions by using graphene encapsulation. So they're going to make a sandwich, as I said before. The graphene is the bread, the cuprous iodide is the cheese, the meat, the salami, the lettuce, the avocado, whatever you want in your sandwich. Whatever your favorite sandwich filling is, that's what the cuprous iodide is. This new 2D material is synthesized directly between graphene layers in a single-step wet chemical process and is henceforth called hexagonal copper iodide, 2DH cuprous iodide. Well, I guess if you are the first person to isolate this phase, you can name it, and if that's what you want to name it, then that's fantastic. We fully characterize the atomic configuration experimentally, interesting, and confirm the stability of the obtained heterostructure by density functional theory calculations. The experimental identification of this material is obtained through a combination of scanning TEM, atomic resolution Z contrast, and pictographic imaging, electron diffraction, X-ray absorption spectroscopy (XAS), spatially resolved electron energy loss spectroscopy, as well as newly developed few tilt tomography. We believe our results demonstrate a route to experimentally access further exotic 2D materials at room temperature. So a whole range of analytical techniques they have thrown at this material in order to understand what it was, and that's going to actually lead to some very pretty pictures which we have coming up here. For example, figure 1. I'm going to quickly look at figure 1, but I actually want to I'm kind of most interested in how they made this stuff. So you'll notice in many of these papers the experimental section, kind of the recipe part, how do they actually do it, is right at the end of the paper. So that's what we maybe will skip to, because I'm actually interested in how they did this in real life. What they're going to go on to immediately after this in the paper is to discuss their characterization. So how do they know that it's 2D copper iodide? How do they know it's not a different form of copper iodide, or the regular form of copper iodide, the cubic form that you normally get? But I do just want to have a quick look at figure 1, because figure 1 looks kind of nice, and they have a normal photograph. So this is what their sample actually looks like, and this is kind of nice. I don't think people often just have a normal kind of optical standard photograph that you might take with a smartphone camera these days, just of what their sample looks like. So this is their reduced graphene oxide film, or kind of graphene layers ready. We'll talk about reduced graphene oxide maybe in a minute, with the 2D layer of what they call hexagonal cuprous iodide in between it. Okay, so that's what the stuff actually looks like. There's a gold TM grid. I mean, I don't know if that's there for scale or just to show. I don't really know why they put that there for scale. But if you don't know how big a gold TM grid is anyway, that scale might not mean much to you. But it's probably a few millimeters wide, that TM grid. They're pretty small. So we've got maybe 10 millimeters maximum, 1 centimeter, about the size of this flake here. Okay, so then we have some microscopic images. And you can, I think, see down here in the highest resolution here, so this scale bar is 3 nanometers, so it's pretty small, and you can see these regions are very strongly ordered, what's going to turn out to be cuprous iodide. So you can see this pattern here of we're actually getting atomic resolution here, so we're actually seeing the individual atoms using transmission electron microscopy. So that's how powerful this technique is. We're seeing the individual atoms here, and as they're going to do later, they're going to compare the pattern of atoms with some simulations to prove beyond doubt, I think, in my opinion, that they have stabilized this phase. So what I did say I would do is go and have a look at the experimental, because I'm actually pretty interested in how they did this. How difficult was it exactly? So I think they've written quite a nice experimental section here. So I'll just read about sample preparation. I don't really care too much about how they did the TEM. Obviously that's important. And if you're a TEM nerd, then by all means go and have a look at that. But sample prep. So the synthetic route to 2D hexagonal cuprous iodide, confined between layers of graphene based on a wet chemical process, was developed by these guys in Bratislava. Okay, first GO. So GO is graphene oxide, so it's kind of an oxidized form of graphene, was produced by the modified Hummers method. So Hummers method is like by far, as far as I know, I'm not an expert on graphene, but this seems to be like the go-to technique for making graphene oxide, which you can then reduce to make something which is pretty much the same as graphene. So they call it reduced graphene oxide, which can be very similar to graphene. It does still have some oxidation, some oxidized groups, some oxygen containing groups on there, as opposed to being just carbon. So pure graphene would contain only carbon. But you know, Hummers method is the go-to way to make graphene oxide. So so much so they don't even have to tell you how to do it, they just give the citation. So resulting 95% of single atom GO flakes, graphene oxide flakes, with a lateral size of 5 to 25 micrometers. 10 mils of water dispersion of graphene oxide at a concentration of 1.5 milligram per milliliter was vacuum filtered through a polycarbonate membrane. A cooled solution at 0 degrees of 20 milligrams of copper chloride, CuCl2. So notice this is copper 2 plus here. So that's quite interesting. They're starting from a copper 2 plus starting material. So obviously that's going to get reduced at some point, because the cuprous iodide that we end up with is copper 1 plus. So they're starting with a copper 2 plus precursor. I wonder if they tried copper 1 plus. I mean, I assume this is the result of probably a huge amount of optimization, this synthetic method. So I'm sure they did do that. But anyway, they start with copper chloride in 2 moles of water. The last step was reduction of graphene oxide by adding 1 milliliter of hydroiodic acid. Okay. HI plays a double role. Okay, so H plus reduced the oxide groups from GO, forming H2O, whereas two iodide ions reacted with copper 2 plus ions, forming the novel 2D crystal structure HCuI. Okay, so we're also getting, they don't actually address the, I don't think so, they don't address the fact that they're actually reducing the copper and they're also reducing the graphene oxide at the same time. So of course the copper is going from 2 plus to 1 plus. So HI is kind of doing both of those jobs at the same time. So they're going to be forming elemental iodine, then, aren't they? Yeah. So elemental iodine is going to be one of the byproducts here from both of these processes. Yeah, you're going to form. I assume you're going to form I2, or maybe you form I triiodide I3 1 minus is another possibility. But I have a feeling you're probably going to form elemental iodine here. Let's see if they say anything about that. I don't think they do. I minus ions reacted with copper 2 plus ions, forming the novel 2D crystal structure hexagonal cuprous iodide. The crucial aspect was timing the process. Okay, cuprous iodide was formed during reaction when the interlayer distance of graphene oxide flakes, 0.8 nanometers, collapsed to 0.35 nanometers, the interlayer distance of the reduced graphene oxide planes. Okay, so graphene oxide is a layered material itself, but it contains lots of oxygen groups on the kind of carbon layer, which means that it has a larger separation. So they're saying here the separation is 0.8 nanometers in graphene oxide between the layers of graphene oxide. But then when you reduce it, when you remove those oxygen groups, you then collapse it to a much smaller distance of 0.35, which is, I think, similar to what you find in graphite. Yeah, so you have different layers. The distance between the layers in graphite, I think, is pretty much 0.35 nanometers. Maybe I'll check that. Should I just Google that? Ask Professor Google. Interlayer distance in graphite. It's not Professor Google. It's Professor Bing. Okay, Professor Bing is coming up with the answer. The interlayer distance in graphite is normally has a value of 0.334 nanometers. Okay, so pretty much the same. Yeah, okay, that's basically the same as what they're saying here. 0.35 nanometers, very similar. The interlayer distance of the reduced graphene oxide planes. Okay, consequently, graphene sheets tightly wrapped the 2D hexagonal cuprous iodide crystals. Okay, the applied pressure of van der Waals forces kept the 2D H cuprous oxide stabilized. The resulting layer was rinsed in ethanol. Sorry, let's scroll down. Rinsed in ethanol. Rinsed in ethanol, separated from the PC membrane, polycarbonate membrane, and dried. Even though between the graphene layers exclusively 2D cuprous iodide is observed, and we saw that in figure 1 earlier on, we'll go back to it in a second, it was difficult to avoid the formation of 3D cuprous iodide on the outer farther from the filter, surface of the reduced graphene oxide film. Okay, it's on the top, and probably in other places in the reaction you're going to get the 3D form of cuprous iodide, the cubic form of cuprous iodide. So what do they do about that? In all experiments, the surface of the filtered film was removed by exfoliation with adhesive tape. Okay, so they remove it by sticking tape on and pulling the tape off, and they're saying that that removes the 3D portion of the cuprous iodide. For electron microscopy, reduced graphene oxide flakes produced by the thermal process were exfoliated under an optical microscope with micromechanical cleavage method using adhesive tape. Okay, yeah, that's kind of what they said. They did it in a microscope. Very, very fiddly, I imagine, to do that, but I think these guys have probably got a lot of practice. Flakes of a few layers in thickness were adhered onto a TM grid by pressing the exfoliating material attached on the tape against the grid. Standard gold TM grid with 300 mesh and quantifoil amorphous carbon support were used. For some samples, to increase the mechanical stability of small flakes, same grids with pre-transfer monolayer graphene were used. Okay, I don't quite understand that. Maybe it already has a graphene layer on there, and then they stick their layered material on top. Okay, then they go into analytical techniques. I don't really want to go into that. I don't think it's kind of super relevant. All right, some interesting points here. So I think the most interesting idea here is that they're using the same method for reducing the graphene oxide to reduce graphene oxide is adding HI, and they're using that to also at the same time reduce the copper chloride CuCl2 to cuprous iodide CuI. And it seems like when they do those things at the same time, they end up with some of the cuprous iodide going kind of between the layers of the graphite or the reduced graphene oxide and kind of getting stuck there. And when it does get stuck there, as we'll see when we go up a little bit further up the paper, it forms this other polymorph, this layered form. That's actually pretty interesting. They don't address directly. Maybe there's some discussion in the paper above. We'll have to look. They don't kind of address that point that the HI is doing. They say the HI is doing two roles, which it is, but it's actually reducing both things. You know, it's reducing graphene oxide and it's reducing the cuprous oxide at the same time. So, I think that's pretty interesting. I wonder if that's actually necessary. If they started off with a copper 1 precursor, I wonder if the thing will work. I'm sure like I said, I'm sure this is very kind of optimized methodology. They didn't just go in a lab one day and do this. This is potentially years worth of work to make this reaction work. Who knows? Maybe they did. Maybe one day they just rocked up and found this methodology. But probably there's quite a lot of I would expect there's quite a lot of optimization which has kind of gone into this. Anyhow, okay, so that's kind of how they did it. So the interesting thing, it looks like, sorry, I keep staying a bit long on this synthesis, but it's kind of interesting. It sounds like all of this was done at pretty much ambient conditions, room temperature. They don't mention a temperature. Oh, they mention they did it at 0 degrees. Okay, so they cool it down. In air, doesn't look like particularly challenging kind of synthetic conditions. It's not like it's done, very high temperature or very low temperature. It's not done in, excluding air from everything. It's kind of, seems fairly accessible technique. Not something that you need really, very advanced facilities to do this. So that's a kind of important advantage, I think, of this. It probably could be done by many chemistry labs, something like this. So if you wanted to try other metals apart from copper, you could probably do that. You could try some other metals, or even, could you do it with other halides? Could you do it with bromide, for example? What would happen? Maybe I'll look at the structure of copper bromide later on. Anyway, let's go look at the pretty pictures, because that's what we're here for. In papers like this, the microscopy is all kind of good. So I like I say, I really like figure 1. They go from kind of the macro image, the optical image you'd see with your eyes, and then they drill down with the microscopy and they get down to kind of atomic resolution. I think that's a really effective way to do this, and you can see here the kind of atomic resolution they have. Let's just read the caption for F to make sure that we understand what they're saying. Scroll down slightly. where is F? So D to F are false colored. Okay, F, atomically resolved had F. So had F is a kind of TM, high angle annular dark field, I believe had F stands for. Close up of a single 2D hexagonal cuprous iodide crystal with magnified inset in the, whoops, let's just move that slightly, in the top right corner. Okay, so this is the highest resolution they have. They pretty much have atomic resolution here. This is false color, as they say. So they're used image J lookup table fire. I think that's a good one for this for this kind of material. And it, obviously this is false color. Electrons don't kind of have color the way that we will perceive color. And these features are far smaller than the wavelength of real light, so they of visible light, so they don't give us a real color image. But I think we can understand the decision to give false color here, and beautiful atomic resolution. That's a very, very striking image of individual atoms of these materials. So let's scroll down. What I'm actually not entirely sure about is which atoms are these. Are we seeing the copper, or are we seeing the iodine? So iodine is much more electron dense than copper. It's much higher atomic number than copper. So I'm kind of expecting that it's the iodine we're seeing here. I'm really not an expert on HADF or TEM, but normally I think when you're in HADF mode, probably electron microscopy, why are you saying HADF? You're probably pronouncing that completely wrong, or people wouldn't try to pronounce it. But I'm going to keep doing it. When you're in HADF, I think the brightness is proportional to electron density. I might be wrong about that. I'm pretty sure that's right. So I would expect these bright dots to be the iodine, which is massively more electron dense than anything else. So carbon, very low electron density. Copper's kind of in the middle. If you think about where it is on the periodic table, iodine very, very heavy. It's going to be pretty. If we're going by electron density, I'm sure these are iodine atoms. Maybe I should read it. Should I read the? Let's read it. Macroscopic quantities, blah 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 blah, shown in Figure 1a. Okay, I really want to see what they say about Figure 1f. Let's see what they say about Figure 1f. The periodicity of the lattice in plane direction analyzed converting. Okay, so they can. Do they have anything about 1f before this? 1. Okay, by selecting particular areas of interest in Figure 1f, separate Fourier transforms were calculated for the graphene and a 2D hexagonal cuprous iodide splitting Figure 1gh. Okay, interesting. The period of second order hexagonal cuprous iodide reflections matches closely with the first order reflections of graphene, implying commensurability of the lattices. For comparison, graphene first order reflection, green circles are indicated in both panels. The average value of the in-plane lattice parameter of the 2D hexagonal cuprous iodide determined from electron diffraction is 4.19 angstroms, which is slightly smaller than the 4.26 angstrom hexagon to hexagon distance along the armchair direction of the graphene. Okay. Alright, so the Fourier transform part, this is let me just scroll slightly better so we have it on the screen. So Fourier transform is a very powerful way to analyze images where you have periodicity. So that means where you have kind of repeating units. So what and that's common of crystals. Crystals are things which have periodicity, which have repeating units for some definition of a crystal anyway. So they're using a Fourier transform to convert this whole image, or this part of the image, I think, into what's called a reciprocal space image. So the interesting thing here, if you look at the scale bar, we have 3. This is what's called a real space image. So the distance here is measured in nanometers, which is just a normal distance. So admittedly, it's a very small distance, but it's a distance the same way that a meter or a mile or a kilometer or a light year is a distance that we can kind of understand. It's just a very, very short distance. If you have a look in the Fourier transform, then what we have is this is what's called a reciprocal space image. So this is a real space image. This is a reciprocal space image, and it's not a typo. The units here are nanometers to the minus 1, or 1 over nanometers, or reciprocal nanometers. Okay, so it's like 1 over distance. So what on earth does this mean? I don't think we're going to go through a reciprocal space tutorial now. It's probably not in anyone's interest. But this is essentially a way to represent a repeating structure that repeats forever in real space as a series of discrete points in what's called reciprocal space. So, for example, this is saying if this distance was this distance is 4.69 per nanometer. So it means every 4.69 nanometers you would have one of these repeat units. Yeah. So if you travelled, so it's like a spatial frequency. So every time you travel 4.8 nanometers, you'll find one of these things, and you travel another 4.8 nanometers, you find another one of these things. So you can summarize that by saying every 4.8 nanometers, you find one of these things. So you have one of these things per 4.8 nanometers, yeah, or 1 over 4.89, 1 over nanometers, yeah. So this is a very, very common way to represent periodic structures. Is actually the reason I think that it's used so much is that when you do diffraction techniques, they kind of let you directly access reciprocal space. So you directly see into this world of reciprocal space, if you like. But maybe more on that another time. They are able, apparently, to pull out the different periodicity of the hexagonal cuprous iodide and the graphene. So the graphene will have its own periodicity because it's an ordered structure. It's a crystalline structure, if you like. It has an ordered and periodic arrangement of carbon atoms, and inside that is another periodic arrangement, which is the copper and the iodine atoms. And they are saying, it's kind of hard to see on these images, but maybe we just have to believe them, that they can see both the periodicity of the graphene and the periodicity of the cuprous iodide, on the same image. Okay, so H, they're saying this is the Fourier transform of the hexagonal cuprous iodide, and G is the Fourier transform of graphene. Okay, so all right, fine. So I think what they're saying, this inner kind of hexagon is the Fourier transform of the hexagonal cuprous iodide, and the larger one in reciprocal space is this larger hexagon is the Fourier transform of the graphene. Now, a larger hexagon in reciprocal space means that in real space it's actually a smaller repeating unit. So the hexagonal cuprous iodide has actually got a larger repeating unit, but in reciprocal space it's got a smaller repeating unit in reciprocal space. Can it make sense? Because it's 1 over distance. So this is one way that they're able to get, I think actually the only way in a paper, they're able to get out the lattice parameters, the repeating distances of the different crystals, of the graphene and the hexagonal cuprous iodide, and they're able to show what the relationship, as well as getting the size of the lattice is, they're able to show what the spatial relationship or the orientational relationship of the two lattices actually is, which is kind of nice. Okay, elemental composition. So they want to obviously prove, and this is quite important for their paper, they want to prove that the stuff inside, the stuff that they're actually looking at, is actually cuprous iodide. So obviously there's other things it could be. You know, they put copper chloride in there, maybe there's some chlorine in there, yeah? They're probably, although they don't actually talk about it, I think they must be making elemental iodine, I2. So how do they know it's not actually just iodine inside? Yeah, and how do they know there's any copper there at all? So they do some elemental analysis. The technique that they use is electron energy loss spectroscopy, or EELS. Yeah, so they show some EELS images here. So EELS is a nice technique because you can do it at the same time or in the same equipment as the TEM, the transmission electron microscopy. So you can have a look at you can kind of compare the HADEF image here, which is what we were just looking at before, and superimpose on top of that the EELS image to give you the chemical composition. Yeah, so you can look at kind of the HADEF, which I think, if anyone in chat, which is 0 people at the moment, is an electron microscope expert, tell me if this is wrong. I think HADEF tells you about the electron density. Yeah, so the contrast is from different electron density. So EELS tells you about the chemical composition, so it can identify where the copper is and where the iodine is. So you can kind of put that on top of the HADIF image, and you can see the bright spots actually kind of correspond to both things, both the copper and iodine. So that was actually my question before. What are the bright spots? Are they copper or iodine? In fact, they might actually turn out to be both. They might turn out to be both. So that's kind of an interesting point. Okay, what else have we got going on? So they use EELS to identify that. They use X-ray absorption spectroscopy, XAS, to identify something to do with the oxidation state. So they look at the copper. This is the copper edge in XAS. So the copper edge means the point where the copper starts absorbing the X-rays. It's absorbed the X-rays because of electronic transitions which go on within the copper. And exactly the shape of this edge, the energy of the edge and the shape of the absorption edge are going from low photon energy here to high photon energy. Tells you can get information about a few things actually, but you can get information about the oxidation state. So they're saying that the cuprous oxide, CuO, sorry, copper 2 plus oxide, not cuprous, this is cuprous oxide, Cu2O. Copper oxide has this kind of peak here. Cuprous oxide has a peak here. So they're saying they have some oxides of copper here, which is kind of quite interesting. I don't know whether the copper chloride has reacted with the graphene oxide, because remember they had a lot of oxygen in their system from the graphene oxide to start with. Maybe that's where the oxygen comes from in this sample. I don't really know. Copper iodide, cuprous iodide, they're confident that they have these peaks here, which they think correspond to cuprous iodide. I'm not really an XAS expert. I would definitely want to go and look this up. Interpretation of these. I think they've done they've kind of done an okay job, I think, talking about this in the oh, it's further up actually where they talk about the XAS, sorry. So let's just see what they say. The copper L3 XAS spectrum shown in figure 3 allows us to clearly identify the cuprous iodide compound thanks to several characteristic spectral features indicated by arrows, reproducing well the results from the literature. Okay, so we could go and look at these if we were interested. The main absorption maximum around 936 electron volts is assigned to 2p to 4s transition combined with 3d to 4s hybridization as detailed in reference 21. The shoulder close to 935 eV is part of the CUI characteristic line shape and has been attributed to valence exciton. Okay, interesting, because you would think, I wonder, following up on reference 22, you would imagine the excitonic structure is going to be different in this 2D layered material. I would think very different in the 2D layered material compared to whatever else they're looking at. So I assume from reference 22, without having looked it up, because this current paper, the paper we're looking at, says they're the first people to make this 2D layered material. I'm assuming reference 22 isn't about this 2D layered material. It's probably about the kind of standard cuprous iodide. So I would think, to be honest, the valence exciton, the excitonic structure, I would think would be very different. So what we're talking about here is the electronic structure, the arrangement of the outermost electrons and the empty electron energy levels within the material. I think that would change probably quite dramatically, going from the cubic structure to a 2D layer structure. So that's kind of an interesting point. I wonder whether that kind of comparison really stacks up to you know, I would want to have a look at reference 22 and see what they say there. Two other features are present close to photon energies of 931, 933 eV that we attribute to two different oxides of copper, copper 2 plus, copper 1 plus oxide. Both copper oxides probably originate from the carbon tape. Oh, okay. They don't think it's from copper interaction with the graphene oxide in their synthetic process. They think it's due to the carbon tape. Fine. Which contains them as we measure separately. Okay. Well, fine. Okay. Maybe the carbon tape does, but maybe, you know, you could use something else to stick down your sample if you know that it's got a load of copper in it and you're specifically doing a copper L3 XAS. I don't know. I think maybe if you really wanted to, I mean, you go to do this XAS, I guess they're doing this at synchrotron. Let me just check how they're doing XAS. Yeah, so it's Electra. So this is a synchrotron in Germany. I think it's in Germany. Um, so I would have thought, you know what? I would have thought that they could have used some other way. The carbon tape is just to stick the sample down. If the carbon tape contains copper, and you're going to a synchrotron specifically to look at the copper edge, you know, maybe you could have done not use copper containing carbon tape. I don't know. I don't want to be too critical of these guys. It's very difficult experiments. What I would say though is it's possible at least, and they haven't ruled it out, I think, in their paper, that some of this stuff is coming from their synthesis. You know, you are reducing graphene oxide. Sorry, you're reducing graphene oxide. The oxygen's got to go somewhere. You've got a whole load of copper around. It's not inconceivable that you that you form some copper oxide of various different oxidation states there. Anyhow, okay. What else do they say? Is there anything else interesting here? Let's just scroll down. As our Cuprous Iodide sample is rather porous film, the signal from its bonding carbon tape, okay, blah, 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 blah. The white line of the iodine M2 edge is certainly present as well, but superimposed by copper oxide. Okay, so they're also going to have an iodine absorption here. Ah, yes, as they show here, maybe. I'm not sure. Seems to be quite different energy, but as I say, I'm not an expert on this. Maybe there's some iodine contribution here as well. Okay, fine. Anyway, let's have a. This is maybe more interesting. Atomic structure in cross section. 3 complementary techniques were further applied to study the 3D atomic structure, cross-sectional imaging. So, how exactly is the copper and iodine arranged within this layer? So they made this sandwich. They made this 2D cuprous iodide. What is actually the arrangement of the atoms within the layer? Well, let's see what they say. Cross-sectional images provide the most direct proof of the atomic configuration presented in Figure 4. Okay, so Figure 4, they have some cross-sectional TEM. So here we go. This is, I think, very difficult to achieve, getting this cross-sectional TM image. So they're saying here is a carbon. Again, this is going to be a full scarlet image. Here is a carbon, and then here, these brighter spots are the copper and iodine. And what they're saying here is that the iodine actually kind of goes on the outside, and the copper is the blue atoms, so the copper are the kind of lighter atoms inside. So again, from the HADF, you can see the brighter the iodine, you would expect to be the brighter spots. Why the top layer is brighter than that layer, I don't know. Again, I guess you can see here that the outer spots definitely are brighter though. So that will kind of fit with the idea that iodine is on the outside and the copper is in the middle. So it's kind of a sub. Let's think of the substructure of the sandwich. So you've got your carbon layers of your bread, and then I don't know, what's the iodine? Maybe the iodine is the butter, like on either side of the bread, and then in the middle is the copper is your kind of chosen sandwich filling. It's your cheese slice, or your vegan cheese slice, or your pastrami, or whatever it is you want to put in your sandwich. So there's kind of a substructure here to this sandwich, yeah. Or you could think of the iodine as the lettuce, and the copper is kind of the meat patty in your burger. But I think the sandwich analogies have maybe gone too far. These, to be honest, I don't really understand these. So C and D. The iodine and copper M edge intensity. So this should be the, again showing you the locations of the iodine and copper. But it seems like the iodine is kind of everywhere and the copper is kind of everywhere above the layer. So I don't fully understand that. The iodine sites on the top row of the HADF panels appear slightly brighter, okay, due to greater overlap of the atoms on those atomic columns. All right, fine. So one important thing to remember, we're not just looking at kind of individual atoms here, we're actually looking at like a huge column of atoms, yeah? So we're looking down a big column of atoms all stacked on top of each other. And they're saying that these iodine atoms at the top are brighter because they overlap better. So that column is more kind of lined up, compared to the column of iodines at the bottom, which is maybe more kind of offset. I don't understand C and D. I don't understand why there's iodine up here. Why is the iodine here? I don't know. Why is there copper here? I don't know. I don't know if that's the 3D form of copper iodide that they said was on the surface. Remember back in the experimental, they said that they formed outside of the graphene sandwich. They formed kind of the normal 3D form. I don't know. Maybe that's what that is. This is a nice part down here. So they talk about they show the experimental images and they simulate what the electron micrograph would look like. Using this simulation software, which I forgot what the name of. It's got quite a cool name. Okay, I can't remember. It probably says it in the experimental. But they can simulate for a given structure. They can simulate what the HADF pattern, what the TM pattern would look like. So, and they use different tilt values here. So they tilted the sample relative to the electron beam, relative to the image that you're seeing. And here at 0 tilt, so we're looking kind of straight down on top of it. This is what the experiment looks like, and this is a simulation. If we had a single layer of this cuprous iodine inside, then they did a tilt experiment, so plus 17 degrees, minus 17 degrees, and here's what it looks like in the experiment. If you had a 1-layer simulation, if you had a 2-layer simulation. So they want to test the hypothesis, do we only have 1 layer inside, or do we have multiple layers inside the graphene sandwich? Do we have single decker sandwich, do we have a double decker sandwich? I said I'll stop doing the sandwich analogies. I don't think it's going to happen realistically. I apologize, but it looks like again, from both the kind of perpendicular, the 0 degree experiment and simulation, and also both of the tilted experiments and simulation, it looks like the experiment matches up very well with the 1-layer simulation, and not that well. It's not a million miles away, but less well with the 2-layer simulation. So I think it's probably not nailed on just from this evidence, but I think combined with the evidence up here, which definitely looks like a single layer, this is definitely, I think, giving a lot of weight to the idea that there's a single layer of this material here. Okay, let's actually look at the structure of these things, because that's kind of interesting, isn't it? This is I think figure 6 is a figure which shows us really about the Dft Calculator Model. So this is the model that the structure that they calculated to be stable via density functional theory, which is a computational method. So they put the kind of atoms into a supercomputer, and they said, supercomputer, do your stuff. Tell me the most stable configuration of these atoms. This is what it came out with. This is what I think they used to model the TM images which we saw above. I'm going to have to read it though to find out. Yeah, the projections which the reconstruction is based on as shown in figure. Okay, that's the supporting information. Reconstructed hexagonal cuprous iodide crystal based on tilt experiments on the top row, and an ab initio optimized structure in the bilayer graphene encapsulated below it. Okay. Oh, right. Sorry, that's the wrong way around. Let me scroll up. Yes. Okay. So this is what they got from the TM image, and this is the DFT. This is the DFT. The bottom one. Yeah, I cut off the top part. This is below is the DFT. Okay. So again, iodine is predicted to be stable on the outside, copper on the inside. That's kind of what they see here. That's kind of what matches up with the cross-sectional TM and with the tilted TM with the simulations we saw below. So this is nice as well. You can see here the kind of in-plane interaction between the graphene, which is the black spheres, that's the bread, and the interaction of the lattices, or the relationship between the lattices in the graphene compared to the lattice in the hexagonal cuprous iodide. So again, a nice kind of relationship here. This is the same point they were, sorry, this, my mouse pointer wasn't there. This one I'm showing here is the relationship between those two lattices. This is what they were talking about when they were up here with the Fourier Transform. Yeah, so this is kind of a real space image of this down here. Yeah, where you have the comparison, the Fourier Transform, the reciprocal space image of the graphene lattice, and the Fourier Transform with the hexagonal cuprous iodide is shown in real space down here, which I think is always a kind of nice comparison for kind of getting your head around the relationship between those. So maybe I think this is probably to do with the reason that this actually works is because these two lattices of these of the cuprous iodide and the graphene have this simple relationship. You could call it like an epitaxial relationship almost, yeah, kind of like the way you can epitaxially stabilize thin film materials on top of a particular crystal structure substrate. Maybe this is kind of what's at play here, that they're able to stabilize because the graphene has this hexagonal structure. They're able to stabilize this this hexagonal cuprous iodide structure here. Okay. So let's have a look at the, let's have a quick look at this. The DFT optimized separation of the graphene and cuprous iodide layers is 3.678 angstroms with a very small variation depending on the interlayer stacking configuration. In the most energetically favorable DFT configuration, iodine atoms are facing the centers of the graphene hexagons. The binding energies are calculated to be 14.1 milli-electron volts per angstrom squared per graphene layer, which is slightly higher than the calculated interlayer binding energy of bulk beta cuprous iodide of 13.4 milli-electron volts per angstrom squared. A single layer of beta cuprous iodide has been predicted to be a direct bandgap semiconductor. Our calculations with HSE06 hybrid functional, which is one of the kind of leading DFT functionals, is the expensive one as far as I know, but they will, again, with if there's DFT experts, feel free to correct me for the 0 people in chat. The HSE06 hybrid functional gave a bandgap of 3.17, okay, for a single layer, and 2.68 for bulk beta cuprous iodide. So maybe not unexpectedly, we see the bandgap of this material predicted, at least. They haven't measured it, so it's interesting. I don't think they do any measurements of the bandgap or any of the electronic properties or optical properties, which is maybe something else they're working on. But seeing as they made it for the first time, it might be nice to do that. But at least their DFT is saying a single layer of this stuff has got a much bigger bandgap than the bulk material, which actually I'm not hugely surprised about. Like I don't know, maybe I'm wrong about this idea, but I really wouldn't have thought that beta cuprous iodide was a van der Waals material any more than, I don't know, lots of kind of, I mean, it's a weakly ionic material. I really would have thought you have ionic interactions kind of throughout. I don't think you have. I'm going to look up the structure in a minute. I don't think you have, layers of iodine kind of facing each other the way you do, in a transition metal dichalcogenide, where you have the chalcogenides kind of facing off against each other with a gap between them. I don't think you have that, but maybe I don't know what I'm talking about, which wouldn't be that unusual occurrence. Band structure calculations further suggest that the cuprous oxide graphene heterostructure, the characteristic linear dispersion of graphene pi bands is what? Let's find out. Is preserved, and a Dirac point appears in the bandgap of cuprous iodide. Alright, so they're saying that the characteristic linear dispersion of, okay, so they're saying the graphene electronic structure is not really affected by having a big wodge of cuprous iodide sandwiched between it. The graphene is kind of doing its own thing. It's kind of chilling up here and down here doing its own thing, and up here and down here doing its own thing, and its electronic structure is not really affected. Whereas the cuprous iodide, compared to its bulk form, is very different, the electronic structure, and even compared to the bulk hexagonal form, as in the layered bulk material, its bandgap is significantly bigger. So that's pretty interesting then. Okay, let's briefly look at their discussion. We spent a bit of time on this paper, so we may bring it to an end soon, but let's have a look at their discussion. The structure different cuprous iodide phases have in the past been subject to some level of controversy. Yeah, absolutely. If you go and look up the different structure of cuprous iodide, there's a lot of different structures, and there was some interesting I think neutron diffraction experiments done probably like 30 years ago, where they were really going into a lot of detail about the actual copper arrangement of copper sites. I think they showed there's a reasonable amount of disorder present in these materials. So the simple kind of the simple cubic, the wort site, the zinc blend type arrangement of atoms, I think, is kind of a simplification. The superionic phase occurring at high temperatures particularly follows from the chemical bonding of copper and iodine that is neither purely covalent nor ionic nature, but exhibits both characteristics simultaneously. Yeah, okay, absolutely. So iodine, we think of copper 1 plus, iodine 1 minus. Of course, iodine is very, very electropositive for an anion. Its electronegativity probably isn't that different from copper. I haven't looked it up. So they're going to have, from even from that kind of very naive standpoint, they're going to have a largely covalent bonding there. There's not going to be a very strongly ionic material. Zinc. So normally the semiconducting zinc blende bulk crystal is the primary phase in ambient conditions, and it transformed into the layered beta cuprous iodide phase at about this temperature here, which we discussed earlier, which we presently attained also at room temperature in 2D form by graphene encapsulation. Yeah, that's what we've been talking about for the last hour or so. The aforementioned controversy, all right, here we go, we have some history now. The aforementioned controversy emerged in 1952 when the van der Waals layer beta cuprous iodide was simultaneously but erroneously identified as a Wurtzite structure. Okay, there we go, that's maybe what I was thinking of then, because I thought that it was the Wurtzite structure, which is maybe not that unusual conclusion, because the zinc sulfide, of course, adopts these two structures, the cubic zinc blende and the hexagonal Wurtzite structure. Okay, by two independent research groups. This error was pointed out by these guys in 1977. But since the authors did not provide the correct unit cell description, the confusion remained, and the Wurtzite structure sometimes resurfaces in the scientific literature. Well, there you go, and also this stream. So I thought that this beta cuprous iodide was in fact the Wurtzite structure. However, first principle calculations imply that Wurtzite phase might after all exist near the ground state. To our knowledge, the beta cuprous iodide phase was first described by Sakuma in 1988 and only later confirmed by Keen and Hull. Sakuma should be rightly credited for this contribution. Okay, the size of, so there's some interesting kind of historical information on controversies about structure of this material. Maybe I'll grab Vesta. I wonder if I have Vesta open actually and look at those things in a minute. The size of the 2D single crystal domains we observe span from a few nanometers, some tens of nanometers, and exhibit high stability under the electron beam exposure, okay, and ultra high vacuum conditions. Okay, that's obviously useful for them because they were able to use the microscopy to image them. Okay, so yeah, let's talk about the actual structure then. We believe the crystal size might be limited by the slight incommensurability of the graphene and hexagonal cuprous iodide lattices. Okay, so we talked earlier, I mentioned earlier how I thought probably the fact those lattices match up very well is perhaps a good reason why this is successful, why you're able to encapsulate cuprous iodide inside graphene, probably because of the lattices are very similar, but they're saying there's a slight incommensurability, so there's a slight difference in size of the lattices, so that might limit the size of the domains you can actually make, because the bigger the domains you make, the more the strain energy you put into stretching one or both of the lattices to match up with the other one. So these are ideas that are commonly found in kind of thin film epitaxy as well. So you have to stretch one of the lattices to make them line up. That introduces strain energy. The bigger you make that domain, the more strain energy you have, and eventually the strain energy is going to be too big to accommodate, and it's going to kind of fall off. You're not going to be able to maintain that structure anymore. So it will break up into other things, or you'll introduce defects, things like that. This likely results in small but significant strain energy penalty, that can be sustained only for a finite crystal domain size, as well as through the appearance of nanopores and voids. There we go, that's kind of what I said. The in-plane lattice constant of 2D hexagonal cuprous iodide crystals measured here is also somewhat smaller than was previously reported for the bulk crystals. Sakuma measured a value of 4.279 angstroms for beta cuprous iodide phase using X-rays, X-ray diffraction, and Keen and Hull 4.304 at a slightly different temperature neutron diffraction, whereas we measured 4.19. Okay, that's actually quite a lot smaller than so 0.1 angstrom, more than 0.1 angstrom smaller. Significant difference, definitely a measurable difference there. For a monolayer using nanobeam electron diffraction at room temperature. What the error on that electron diffraction might be, I mean, or they quote the error here. Okay, so the error, I mean, if that's one standard deviation, I don't know if that's one standard deviation or three standard deviations. If that's one standard deviation, then for sure these numbers could all be the same, I think, within error, so maybe there's actually no difference. Even if it's three standard deviations, it's almost the same. I wouldn't maybe put too much significance on that. The apparent discrepancy might be due to thermal expansion temperatures. Yeah, absolutely, of course. So, I mean, you're doing room temperature versus 655 Kelvin, and actually your difference is pretty small anyway. So I'm not too worried about that. This value also matches Dft calculation and predict 4.2 angstrom spacing for both monolayer and bulk crystal without the graphene envelope. As we also pointed out by Sakuma, each atom in this particular crystal structure has exactly 3 neighbors, and the crystal belongs to the P3 bar M1 HM space group. Okay, to our knowledge, the hexagonal cuprous iodide crystal is one of few one-to-one stoichiometric 2D materials within this particular symmetry, hexagonal bond nitride being the most well known. And besides PBI2 is the only one that incorporates also a halogen atom. Okay, well there's some interesting trivia for symmetry 3D space group fans. Cuprous iodide is one of the only binary materials with a 2D structure within this space group that has an iodine, that has a halide anion. One of the only other ones being lead iodide. So there we go. That's kind of exciting, isn't it? The discovery of 2D hexagonal cuprous iodide is particularly interesting since magnons and layer structure dependent ferromagnetism have recently reported in chromium triiodide, and a host of further magnetic ordering phenomena have been predicted in other 2D metal halides such as this and this. Although DFT simulations have suggested the possibility of exfoliating some of these compounds, the thermodynamic stability under ambient conditions remain untested. Okay, in terms of magnetism, I mean, here we have D10 copper. I don't know. Do we expect magnetism in D10 copper? So copper 1 plus is D10. It's got a filled D shell. I don't know. I mean, I guess we're using the ionic approximation there, so maybe that's wrong. Do they say anything about magnetism from the DFT? I don't think they do. I don't think they say anything about magnetism in DFT. Yeah, I don't know. They kind of talk about other layered materials are magnetic, so maybe our layered material is magnetic, but I don't know. I'd expect some counterpoint to kind of the obvious initial thought, which might be naive and wrong for sure, that D10 copper iodide probably isn't going to be magnetic, but I don't know. What do I know? Finally, there's no reason to believe that the present synthesis approach, which was here used to stabilize crystals of 2D cuprous iodide from room temperature experiments, would be limited to this particular structure. Quite the contrary, we've already applied the same process to 2D silver iodide and nickel iodide crystals, both of which are shown in figure S14, supporting information. And generalizing this concept should allow access to further exotic layered structures, vastly expanding the currently available library of 2D materials and their incorporations in devices and structural properties to be studied at room temperature. Okay, I think that's some good points. I think that their synthetic method looks very accessible. You could just swap out the copper chloride for something else, for silver chloride, for whatever you wanted, and just kind of see what happens. So I would kind of agree with that conclusion. I think that the formulation, there's no reason to believe that it doesn't work for other things. Okay, I think that's almost it feels like it might be a little bit evasive, like saying there's no reason to believe it doesn't work. Actually, they do give some other examples, the silver iodide, the nickel iodide, which it apparently works on. So that's kind of nice. So I thought there's some really nice stuff in this paper. The microscopy looks really, really interesting, I think. The microscopy, I think, fantastically difficult experiments to do these TM images, to get these. There were some things that you could point out. For example, their interpretation of the XAS, where they say the copper Oxide comes from the carbon tape. I mean, you maybe use different carbon tape. It would be really nice to see some properties of these things. So they predict the band gap. As far as I can see, they don't measure the band gap. They don't measure any optical properties. They don't measure any electronic properties. That would be really nice to see. But they do predict a lot of these things from DFT. So there'll be some information there. The method does seem quite flexible. You can maybe use it for other materials as well. That they go on to give some examples. But there might be, you know, a lot more scope to expand that. Interesting historical stuff, if you like that kind of thing. Structural controversy, starting in 1952. That's the kind of, you know, that's the kind of thing you can spend a long time digging through old papers if you really want to know about the structural controversy. So I might follow up on some of these papers later. So I think we are going to draw. I realised I never put any music on the entire stream until now, but we're going to have some kind of exit music. I thought this is a very nice paper. This paper is open access. You guys can take this. You can take this title, you can stick it in Google or Bing, your favourite search engine, whatever that may be, and you can read this paper yourself and have a look at some of the science and see if you agree or disagree with my comments. Beautiful paper, really nice work. Could be a really exciting way to get some new kinds of 2D materials. And we know how big they've been in the last kind of 20 years since graphene kind of exploded. So very nice bit of work from these guys. As I say, look up, you know, have a look at the rest of their work. The main authors based in Austria, authors based in Germany, Belgium, Slovakia, and France as well. So real European effort from really nice collaboration here. And you can kind of understand it. There's a lot of detail synthesis. That synthesis probably took a long time to get right. There's a lot of really specialist characterization. You know, getting this TM, like I said, this kind of stuff is not trivial. And the XAS as well, and the DFT, the calculation. So really nice bit of work. And yeah, I think we are gonna draw the stream to a close after that paper. Do you have a few more papers lined up? But I think for the first stream, one paper is enough. So thanks for watching, guys. If you're watching back on the VOD and you watch through the whole the whole stream, then thank you very much. Really good to have you here. Stick some comments in if you have any comments about how this could be better, articles you want to look at. You know, feel free and put those comments in the chat. In future streams, we get a few live members of in the audience. It'll be really great to have some comments on the stuff that I'm going through. But for now, I will say goodbye to you guys, and I will see you on the next stream.